about that.
Nope, I have not.
You haven't, yeah. Like 0, 1, 2, or yeah, 3, 4, 5.
I like the 4.
Yeah.
But yeah, so you can go up to what, 2 to the 10th.
Yep.
On a hand.
Yep. But not hexadecimal. You cannot go to F.
Doesn't work in hex.
Tell me you can't whip out some toes.
So we're gonna get
Take off your shoes and Crocs.
The first thing I want to show is how many videos is actually on my channel, and the answer is, as of now, 1,579. They're not all mine, okay? Because we do have like 3 or 4 professors using the same channel, but the majority is mine. So I would say about 2/3 of those at least are mine. But I don't bother to organize or index or describe those things, so it's impossible to actually look for anything.
Well, that's nice.
All right. So I'm just going to upload my the class from the class before, so this way I can.
How many gigs is usually one recording?
Well, take a look. 1.7. So one lecture is 1.7 gigabytes.
And
Well, they compress it a little more.
and YouTube just lets you like upload all of those.
If I bring customers, yes, sure, why not? I'm no Justin Bieber, but at least some people watch it. I don't want to be Justin Bieber either.
You almost get the hair.
Just to clarify, I don't even know what my hair looks like. I have heard that I don't have much left, so that's not much to worry about. All right, so let's go ahead and get started with your homework assignment, okay? Because some people said that this is really brutal. I spent like 2 days to work on this. Okay, so let's do this. Let's pick out the most nasty one and then work on it, okay? Because I do want to work on it, because if you're spending like 2 days to work on it, it's, there may be something that you can do that can speed it up. Yep.
I'm not sure about anyone else, but like the nastiest one for me was like the calculating the Z2 plus carry. Like I meticulously expanded it, but unfortunately when I was laying it out
You have to simplify as you go. That is the key, is to recognize things that you can simplify.
Yeah.
Let's do it. Let's go. Let's do it.
Are we recording?
Are we recording?
Hand
screen.
That's a good one. That's a good question. Yes, it seems to be recording, and yes, it is recording.
All right.
Okay. Good. Very good. Checking with that. All right. So the first thing we'll do, hopefully it won't take the entire class period, is to talk about this. Now, I can just do this, right? I mean, I'm done. Scroll through this whole thing because it's all getting screen recorded. Okay, let's move on and talk about something else.
Really?
No, I don't want to do that. Okay, so I'm not going to do that. It's hidden from you, so you cannot see it. Not yet. But what I want to do is actually go back step by step and talk about how to solve that problem, okay? If you already solved the problem by yourself and you think, I just spent half an hour and it's all done, well, I'm sorry, you're going to be a little bit bored for the first half of this class. But that's okay. And we'll go through the preview. And I'm going to skip to the one that really is applicable in this case, which is, we are on the right slide already. Okay, so of all the equations, it looks like this one is bad, which is the last carry flag, but that's not the case, because C is easy to deal with. C is nothing more than just conjunction. It doesn't really make things really bad, okay? R is the naughty one, okay? So we have to deal with the R, especially when you have R inside the R, or one parameter R has a bunch of disjunctions. That makes it really bad, because you have to take the negation of that first and then multiply or take a conjunction with that with something else. So we'll work with the nastiest of these 4 guys, which is this guy here. This is the worst, okay? All right. And I will work on this using mousepad is okay. Or I can just use an HTML editor in Moodle. Okay? That may be even better because that way I can record my actual work as I work on it. Okay, so you have to turn on editing because I'm actually adding an item onto Moodle. And I'll just make it a regular HTML page. So this way I can use color highlighting if I need to. Okay, so I'm just going to call this the derivation of Z2. Sounds like a movie title. Okay, this is the nasty thing. Okay, first thing is you have to be really careful. You have to be able to identify which two are parameters to the R function. Okay, because if you misread the parentheses, then you're going in the wrong direction to start off with, which is bad. Okay, so you got to be really careful. The first, you can work your way from the inside out, or you can work your way from the outside in. It doesn't matter as long as you do it carefully. You can do it, you can mix and match. Okay, that part does not really matter. Okay, so let's unboldface this. Okay, can everybody read this? Okay, I mean, is the font large enough? Is that okay? People in the back. Okay. All right. All right. So let's go ahead and start with this. And the way I do it is I just copy and paste and change the parts that I'm working on. Personally, I like to work my way from the inside out. Okay. In other words, I take care of the C first. The C are the easy ones. So I take care of the easy one first so that they don't become too much of a problem, especially from the notation perspective. So I look at this chunk here and go like, hey, that's just a conjunction of CF. All right? Turn it into CF. And you might say, but that doesn't really help. Okay? Well, it helps in terms of notation. I just got rid of 2 parentheses. Makes it easier to read. I look at the other one, which is over here. Okay, that's a C also, which means it just turns into BE. Okay, and I start to use the notation that I use in class for electrical engineering, not a C symbol. Turn this into a plus, and I don't try to do too many steps in one single derivation, because then it's harder to go back and track down, okay, it's not working, which step has a problem. Because if I try to do too many things at the same time, it's no longer obvious what I did. So I just do 2 things that are really obvious. These 2 are kind of parallel because they don't really interact with each other. Okay, so I'll just say, okay, I'm done with this step. I copy and paste, and then go like, what should I do next? Maybe I'll just take care of this RBE, okay? All right, so let's go ahead and take care of the RBE here. Before I replace it, I'm gonna say, okay, this is B not E plus not BE. Then I go back and say, okay, I just took care of this. Done. Are we okay so far? Are there any questions about what I just did? Now, for those of you who really want to be able to track down what we did, you can use highlighting, okay? In your own editor, if you use Microsoft Word or some word processor, boldface, italic, change the color, underline, and stuff like that. So you can easily highlight for yourself, not for me, because I don't collect this part, right? You can highlight for yourself and say, okay, how did I go from here to here? Even if you make a mistake, it makes it easy to spot the mistake. Okay, I probably will make a mistake or 2. I do not memorize exactly how I derived the whole thing. Okay, so now we can go to the next step. I can expand the other one too, the other R over here, because it's all by itself. I can just deal with that. So this becomes A not D plus not AD. Okay, any questions? Okay, there are no questions. Then we move down here, and I will go ahead and take care of the C first. Okay, inside over here. So I'm going to look at this and carefully match the parentheses. In other words, I want to make sure that I understand this is the first parameter to this C, the carry function, and this is the second parameter to the same carry function. Okay, because if you mismatch the comma and stuff like that, then you end up with the wrong structure of equation to begin with. Then the rest is just a waste of time. Okay, so now that I am fairly sure that that is the case, this is what I do. Because I know this is a conjunction. C is just a conjunction. So what I do is I use open paren, close paren, open paren, close paren to set up a conjunction, and then I copy and paste the parameters into the parentheses. So this way I cannot mismatch parentheses. Yep.
I think you will have missing close parentheses after BE.
Missing
No.
close.
Because it starts
That's a
after
comma.
R, it's opens.
It's a comma.
That's a comma.
No, go all the way back where the first R.
Okay, what is back?
Capital R.
No, yeah.
You see? Now go forward more, and right here after BE.
This BE?
Yes.
No.
Don't you see open parentheses right there after capital R?
Yeah, and then the closed
Look at the
parentheses on
first
the
line.
outside.
The whole thing is within one R function.
Yeah. There's a comma right after
This
not
is-
But
AD.
the C is in
Yes, it is.
This
The
is
C
the
is
first
within the
parameter
second parameter.
to the outer R. This whole thing is the second parameter to the outer R.
Yeah.
Yep. Okay, so getting back to here. So I just copy and paste the first one over here, copy and paste the second one over here, and then I say, okay, now I got this taken care of. Get rid of it. And that's how I do it. Okay, this is exactly how I do it. I do not memorize the steps, so if you look at the other C2, it's going to be a little bit different, okay, because I changed the order maybe a little bit here. So now I got two terms and one single R left, but that's the nasty one, okay? Because remember, with any R, you have to do the conjunction thing, but it separates into two conjunctions with a negation to each individual component, depending on which one you're talking about. So, and this is the one step that I think is going to be helpful, because the way I set this up is I do this first. In other words, I make the structure first, and then I go back and fill in the structure. Because when you fill in the structure, it's just copy and paste. Okay, it's difficult to make a mistake. You can sometimes, if you forget to select one of the closed parentheses, yes, you can make a mistake, but it's harder. So in this case, what I do now is I take the first parameter, just like that, and I say copy, paste it here, and then paste it here. The second parameter is nasty, but you know what? I don't care, okay? Because all I'm doing here is copy and paste and paste. Yep.
Would it be useful to simplify the second part of the parameter? The second parameter, the B not E plus not B E CF.
Well, I just, I turn it into this form first, and then I start it. I guess you can do it that way too. I'm not saying that this is the best way to do it. I'm just saying this is the way I did it. So you might use a different way to do it, and it works out better for you. But there are different ways to do it. Okay, so once we get to here, then we can do some real actual work. Okay, so I can actually start to expand something, and I like to do things from the inside out instead of from the outside in. That's just my personal preference. So I look at this term here and say, okay, I only want to focus on this, okay, nothing else for this one, okay. And as you can see, that term is also over here. So once I expand it, I can reuse it. So what I do is I just do it on the side, okay. I just take this term here, and if I worry about forgetting which term I'm expanding, I just use one of the many methods to remember, okay, this is the one that I'm working on. I can change the color, okay, so we'll just go ahead and change the color and say that, okay, this is what I'm working on, and we'll go ahead and expand it, okay? So this is just distribution. So when you expand it, we end up with B, C, not E, plus not B, C, E, F. Okay, I'm forgetting an F here. Okay, double check. B, not E, C, F. B, not B, E, C, F. Okay, but you can also see that I'm reordering the individual variable so they're all in the same order. Okay, because that will help me later on to spot things that are similar. Because the natural tendency is just say B not E C F, not B E C F. Okay, but that doesn't really help a lot when you need to find out. Okay, but can we simplify? This is much more helpful when I need to simplify. Okay, so knowing that the red portion becomes this, and if I want to, I can also label this one red as well, just to say that they are really the same thing and they can both be replaced by the expanded form of this one. Okay, so now I just copy and paste and get rid of, okay, first of all, select, copy, and then I know this whole thing is just replaced, this whole thing is just replaced. Are there any questions at this point? In other words, have I made a mistake yet? No? Okay. It's still not too bad, okay? The bad part has to do with this guy here. Because essentially what we're doing is we are trying to push the negations all the way to individual variables. We don't want to negate a conjunction. We don't want to negate a disjunction. We want to negate only individual variables. But what can help us with those things? De Morgan's law. Because every time you apply De Morgan's law, what are you doing? You are moving the negation one step into the inner part of the equations, of the formula, right? So that's what we're doing. We are basically just moving things in and in and in until they cannot be anymore. Okay, so now we're looking at this one here. And then we say, we have a negation on the outside, and then we have a bunch of disjunctions on the inside. But we can look at all of those disjunctions as just one single disjunction, and then we can apply De Morgan's law. Now, but this is also the tricky part, is when you apply De Morgan's law, in this case, you have to negate each individual term, okay? But you also have to remember they will be now joined by conjunctions. So you will have negation of something, conjunction, negation of something, conjunction, negation of something in this case. All right, so let's go ahead and work with this one. Once again, copy and paste. And so we basically say, okay, we don't like this disjunction on the we don't like this negation on the outside of a disjunction. So we basically take care of this, negate it, negate this. Okay, now it is important to put parentheses now because we are negating the entire conjunction, not only the first term of the conjunction. Okay, so we are applying the negation to each individual term and we turn all the disjunction into conjunction. Are we still okay so far in terms of concepts? The application of De Morgan's law. Still okay? All right. And I'm not going to do anything else because this is a relatively big step. If I make a mistake, I want to be able to spot it. So the next thing I do is to go like, okay, might as well just take care of this, okay? Because this is a negation applied to a conjunction. We can apply De Morgan's law again. So now we just copy and paste it and say, we'll turn this one into, we'll distribute the negation into the inside, but then we have to change the conjunction into a disjunction. Same thing with this. Put the negation in the inside, negate, 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 and then turn all the conjunctions into disjunctions. Yes, I am using double negation here, but I can deal with it later, okay? In other words, I'm just mechanically doing something, and then I come back and clean it up later, okay? Because it's important to not to mix in, when you're mechanically doing something and doing the simplification. So I will separate the simplification to the next step. Okay, same thing here. Negation puts into here, 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 and here. Turn all the conjunctions into disjunctions, like that. Are there any questions at this point? It's looking pretty bad now, okay? But it gets worse. Because when you have, well, this is pretty much the almost at the climax, okay? This is almost the worst part of this. Because when you have the cross product of 4 terms with another thing that has 4 terms, you end up with 16 terms, okay? Maybe. Okay, now I go back and say, okay, can we do any simplifications? Well, maybe not a whole lot, but at least I can take care of this. Okay, let me change the screen size here so we can scroll up. Because people in the back, probably cannot see the bottom row that well. There we go. All right. So we go back here and we say, oh, now my screen doesn't match. It doesn't want to get any smaller than that. Okay, but it's okay. I think I can work with this. Copy and paste. So now we look at double negation. Oh, I just took care of one. Okay, let's take care of the other one. Double negation goes away. Okay, so it looks like I cannot do any further simplification. So the next step is to say, okay, since I cannot do any simplification, maybe I'll just go ahead and carry out one of the distributions, okay? I'm going to pick out the easy one first, okay? Which is the 2-term and the 4-term. I'm not going to pick on the 4-term and the 4-term. Because maybe I can simplify something after the 2x4 expansion, so I don't have to actually deal with a lot of items later on. I don't actually remember which step works out better. I'm just doing this as a heuristic. So we'll go ahead and expand these 2, okay? We take care of these 2. Now, my trick of doing the expansion is, once again, do the structure first, and then copy and paste. Okay, so let's see what I mean by that. Okay, so when you expand these, how many terms do you end up with? You end up with 8 terms, okay? So we just say blah blah plus blah blah plus, whoops, blah blah plus blah blah. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay. And that will take care of the first expansion. Now what do I do? Well, we look at this thing here and say, this will go to 1/2 of those things. Okay? So we just copy 1, every other one, 2, 3, 4. That goes to the other half. 1, 2, 3, 4. Then what do we do with the other one? It's 1, 2, 3, 4, and 1, 2, 3, 4. So this one, I think copy and paste is going to be slower than just typing it. So not B, not C, E. Oops, I think I made a mistake. Every other one. Okay. Every other. The nice thing about an editor is I can do this. Okay, so we got B and E, and then it's. Okay, I got it. So not B. Skip to this one. Not okay. Not B and then not B. Okay, there we go. Not B, not B, not C, not C. E and E, and then not F, not F. There we go. Not F, not F. All right. Is that okay? All right. But you can see it's kind of mechanical. And the whole point is to make it as mechanical as possible. Because when you do something mechanically, you can make mistakes, but those tend to be mechanical mistakes, and they're easier to track. Okay? I just thought of this. Maybe somebody already thought of it already, which is okay. Did anyone do a screen recording when you're doing this? Why would you want to screen record yourself if you're not going to publish it? exactly, you can trace your way back and say, how did I come up with this term? Step by step. Now, if you are by yourself, or you can actually record your voice and your reasoning, it's even better. Because you can hear yourself and say, okay, I'm applying the Morgan's law, but if the end result is not actually the application of the Morgan's law, you just cut yourself. Okay? I just thought about it, I try to do something like that when I manage servers. When I do something, I just screen record the whole thing. So if I mess up, I know how I did it. All right, so now we can do some simplifications. So once again, copy and paste. Okay, I can see some terms that can be simplified, like this one, not B and not B. Yes?
Are we not considering the third term?
The what?
The third term.
The third term?
Yeah.
You mean this guy here?
No.
Oh yeah, I forgot the parentheses too. Yep, you're right. I forgot about that. I need to use extra parentheses. So we start one here, and then it ends here. Is that what you're talking about?
Yeah.
Okay. So put one here, and we'll put one here. There we go. Okay, but now we can do some simplifications. Not B is just not B. Okay. This one we cannot really simplify, but we can just get rid of the unnecessary parentheses. This one we cannot simplify yet, get rid of the parentheses. Okay. This one we can just reorder. Okay, so it looks a little bit better, and we can do the same thing here. So I'm just reordering things and getting rid of the duplicate items. What about this one? Not E can never be true at the same time. Okay, because either not E is true or E is true, but one of them has to be false. In a conjunction, if at least one is false, the whole thing is false. So this one is guaranteed to be a 0. But plus 0 itself is also useless, so you can just get rid of it. Okay, not B, not F, not E, not F.
You deleted an F there.
Yeah, you did. You deleted it.
Oops.
It was not.
After the exclamation mark.
We
Not
have
B, not
Control
F.
C.
Oh, not B, not F. Okay, there we go. I can see how a screen recording can be helpful, because I can just go back. So that's what I did. There we go. All right. So out of these terms, okay, so we just make this one step because I want to separate the next optimization from this one. We can further simplify, because if I have not B already, anything else that also has not B, we can just get rid of it. Because the whole thing is a big conjunction, right? The whole thing is a big conjunction. If I have this not B here, which is, can I have a case where this expression is true, but not that expression? In other words, can I have not B, not E being true, where not B itself is false? It's not possible, right? Because in order for a conjunction to be true, both components of the conjunction has to be true. So that means if not E is true, not B itself has to be true. Why is that important? Because if I have a disjunction here, it means not E is useless. You can put it there, it is not incorrect, it's not wrong, it's just an extra term that doesn't do anything. So right here, I can do some real simplification. This term, gone. This term, gone. This term, oops, gone. And this term, gone. So I went from 8 items down to 3. Is that okay? Are there any questions about what I just did? Well, yes, go ahead.
Can you show us how you did that with the 3 sets?
Mechanically or mathematically? Mathematically. Well, it is actually kind of explained in the homework description itself. But basically what you're looking at is some kind of expression A, or some kind of expression A conjunction with B. Okay? This is what we're looking at in terms of just the mechanical aspect of it. But what is A? A is the same thing as A and true. Okay, can we accept this? A is the same thing as A and true. Because whatever and true is just whatever. True is the identity of conjunction. Is that okay? It's just like times 1 in multiplication. Okay? Plus AB. Okay? And then I can reverse the distributive law and say this is the same thing as A times, or A conjunction 1 disjunction B. Is that okay? I'm just reversing, the distributive law here. Okay, I went from the distributed version to the condensed version. What is 1 plus B? What is true or something?
True.
1, exactly. True or something is just true, because in order for a disjunction to be true, you need at least one side to be true. If one side is guaranteed true in a disjunction, the whole thing has to be true. There's no other way. Is that okay? But what is A1? It's just A. So is that okay? Does that explain, how we can do all that, simplification? So we took out 5 terms because of this one little simplification rule. So now we look at this mess and go like, well, I guess there's no other way except we have to now take care of this particular distribution. Okay, so we'll go ahead and take care of that one. So in this case, we'll end up with 12 terms. So we have 1. Well, okay. So we end up with 12 terms. We can say just 11 pluses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, 11 pluses. And the way we do it is we have to do this one for every 4 of the other ones. So we have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then the same thing here. Okay. Let's see.
Looks a little off.
Hmm?
It looks off.
It looks off?
Yeah.
Oh yeah, the pluses are. There should be 11 of these, and there are exactly 11.
The
I'm
third
leaving
one.
this one for this guy, leaving this one for this
I
guy.
believe it's the third one, and subsequently.
Okay, I think I have a better way to do this. How about we take this, and then we just repeat it 4 times.
All right.
2, 3, and the 4th time is just the original copies. Then we just say that we will put this B in front of everybody here, put the not C in front of everybody here, and so on. All right, so this one has B in front of everybody, B and B. This one has not C in it, so it's not B, not C, not C, not C, not E, and we have not C, not E, not F. This one has not B, not E in it, not E, and we have not E, and the last one has got not F, so we have not F, and again not F. Okay, I think that works out, and then we don't need. Nope, that all works out because I have. Oh, we don't need this part more. So we get rid of that one. Okay. Is that okay so far? How the terms are expanded. Okay. So I leave this one as it is. Okay, because in case I did some mistake expanding, I want to know how I expanded it incorrectly. Now I can simplify again. What is that? B not B. 0. But 0 can be just eliminated. I don't need that anymore. This I cannot simplify, not yet. These I cannot simplify. This one I can get rid of one of the not C's because not C is just not C, so I can get rid of one of those. Same thing, get rid of one of the not E, get rid of one of the not E, get rid of one of the not F over here. Okay, so I just call that one step, move on to the next step here. Okay, what else can I simplify here? Are there any terms that have common components? Or is one of the terms appearing all over the place? We see several things, right? Okay. So let's see what we can do about this one. Well, okay, the first one I noticed is not B, not C is over here. But this component has not B, not C, and then something else. What do? Get rid of it, because it doesn't serve me any purpose. So we're going to do the same thing with all of the other terms and see what we can do. Okay, we have not E, not F here, and then we have an exact duplicate over here, not E, not F. This one has not C, not E, not F. We can get rid of that too. Not E, not F is a part of this, so we can get rid of this term. And not E, not F is also here, so we just get rid of this altogether. Okay, save it. Move on. Can we do any more simplifications?
Don't you have that on C, not E?
Not C. Again?
Don't you have not C, not E on the multiple places?
Oh, there are two not C, not E's. Okay, very good. Duplicates. Okay, so we'll take care of the not C and not E. So we have to keep one of them and just get rid of the other one. Okay, very good. Any other thing we can simplify here? I think that's about it. Okay, that's all we can do to simplify it. Okay, so now we can go ahead and expand the AD onto the B, C, E, F. Okay, and it's guaranteed that we cannot do any simplifications in that case, because the terms of the first destruction only has A and D. The terms of the second part only has B, C, D, and F. So there's no way we can actually simplify because they don't. The same symbol does not occur more than once in the same conjunction, which makes it kind of difficult to simplify. There are ways to simplify, but we'll see. So once again, the way we do this part when we expand is to copy and paste this twice. Okay. Copy, paste. Okay. The rest of the equation is still the same. I'm not going to deal with that just yet, so we'll keep that one just the way it is. And then we can just go ahead and append this part to the first part, and then append the second part to the other part. Control C. Okay, let me just double check. So we should end up with 6 terms. Okay, so we have okay, we have all the 6 terms here. Okay. Yep.
Is there a pattern here, like if you're doing 4, 5, 6-bit adders? Is there like a pattern, or do you just have to keep on expanding and expanding and expanding?
I don't think there's any particular pattern. I think that's you're yep.
Though if there was a pattern, it'd just be more nested stuff inside of nested stuff.
Not the answer.
You asked for a pattern, as depressing as it is.
Okay, so now we have expanded everything out of those terms. Anything that we can actually simplify? Yep.
Can we go to the fourth implies in the bottom? Those 3 terms, B,
these two. Hmm? Sorry?
The one below?
The one below?
Yeah, that one.
Here?
That one's
They are the same as these three. We got rid of B, not B, because it's a 0.
yeah. But then from the highlighted part, go to the next.
From the highlighted part, sorry, I couldn't catch your end.
From the highlighted part to the next.
To the
Next line.
to the next line.
Yeah.
From here to here. You mean to here?
Yeah.
How do we get from there to here?
Yeah.
Okay, so we. Okay, we saw the not B, not E here, right? This one is not B, not C, not E. So we get rid of the one that we don't need. Okay, let me just double check.
Is that not B or is that regular B?
Hmm?
The one that's highlighted. It looks like a regular B from here.
Oh, that's a regular B. Right. And so screen recording is handy because now I can actually go back in time and figure out what I did.
Not C, not E's there, right? So, same concept because of that.
Say that again?
Because the not C, not E, instead of not B, not C. Like it's the same concept, but it's not C, not E.
Yep,
instead.
it is. So because of this, we can eliminate this term. Yep.
So even if there was a mistake, it's been erased.
Well, I cannot remember how I did that.
Yeah.
Okay, so how about this term here? We got rid of it because of not E, not F. So that's how we got rid of both of these terms. Okay, so there we go. I'm pretty sure I said when I did it, but I cannot remember when I after the fact. Okay, so let's go ahead and take a look at these guys and see if there's anything. Well, okay, let's expand this part here. So this part can be expanded, but before we expand, there's something we have to do first. This negation only applies to this disjunction, so we have to do this part first. Okay. Control C, Control D, Control V. So now we have to move the negation into the inside, turn the disjunction into a conjunction, like so. And then we'll go ahead and apply De Morgan's law one more time. So this time we'll take this negation, put it into here and here, turn the conjunction into a disjunction, take this negation, put it inside, turn the conjunction into a disjunction. And then we can actually do some simplifications here. Not is just that. So now we have not A or D, and then A or not D. Then we can go ahead and expand this one. This one can be simplified a little bit. Because with this one, we end up with not AA plus not A, not D, plus DA or AD plus D, not D. And out of these four terms, 2 will be simplified. This one is gone because it's D, not D. This one is gone because it's not AA. Okay, so both of those will reduce to 0. So we now only have not A, not D, plus AD, and then the other terms. This particular distribution probably cannot be simplified any further because one side only has A and D, the other side only has B, C, D, F. So it's unlikely that it can be simplified any further. But we'll go ahead and expand it and figure out how many terms we'll end up with. So once again, copy, paste, and then we copy and paste the first term in front of everybody here. Copy the second term, and paste it to everybody on the second side, like that. And then we can get rid of the actual multiplication because we just took care of it. So that's the final result, and I think that adds up to 14 terms. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 terms. So I think there's probably some terms that can be simplified and that did not simplify.
I kind of got like 30 terms.
I got 32.
You got 32?
Yeah, same here.
I think I was able
Okay,
to
we're
get-
not competing here. We're not competing here. Okay, so this would be a valid answer. Okay, well, assuming it is a valid answer. So now, how do you do a sanity check and see whether this makes sense or not?
You just test it, and if it fails, just
You can test it and see if it fails.
try
You
again.
can also do one other trick. Okay. So the other trick that you do is you look at each one. Okay. So, okay, let me just pick one of them, and let me ask you what. I think some of these can be simplified. I'm just too lazy to do it.
One thing is to make sure that there's not one whole set of conjunctions that has only knots, because if there's all knots, then that means 0, 0, 0,
Right,
0,
exactly.
and 1.
Yep, but that's what you can do. Okay, what is A, B, C, D, E, F? Because by this time we have all forgotten what the original problem was,
X 0, Y.
right?
0.
And that's the problem because we have forgotten. We have forgotten the context of what this really is. What is the result? What are these A, B, C, D, E, F? The result is Z2, okay, which is one of the bits of the sum of two numbers that we are adding. A, B, C are the 3 bits of the first number. D, E, F are the digits of the second number. Why is that important? Because each one is telling you one particular case where the most significant bit is going to be a 1. We can check whether it makes sense or not. So let me explain what I mean by that. Let's take a look at this one here, okay? What does it say? Okay, I'm going to do this on the whiteboard. It says A, right? Not B, and then we have a not B, and then we have a not C. That's it. Okay. When you see something that is non-negated, it means it has to be a 1. Okay. So now we end up with a 1. If you see a negation of something, it has to be a 0. When you see something that is negated, is that B negated? Yes, it is. So this is negated, it means it has to be a 0. Oh, but what about E and F? It doesn't even mention it. It means it can be anything. So we just say question mark, can be 0 or 1. Doesn't matter what it is. So you add up these two numbers, even with some unknown bits, and then you ask yourself, is Z2 guaranteed to be a 1 in this case? 0 plus whatever is just whatever. 0 plus whatever is just whatever. Are we going to carry in any way? No, because 0 plus something cannot carry, cannot generate a carry of 1. Then we have a 1 plus 0 guaranteed to have a 1 in the result. So in other words, I have just shown that the first term makes sense in this context. What about the second term? Let's take a look at the second term here. The second term is A, unknown, and C is here, so C is a 0. So, okay, let me rewrite it. Okay, A has to be a 1. B is not mentioned. C has to be a 0. D has to be a 0. E has to be a 0. And F is not mentioned. Okay. So you look at these two numbers. X represents, it can be a 0, it can be a 1, we don't know what it is. 0 plus X is whatever X is. X plus 0 is whatever X is. 1 plus 0 is guaranteed a 1. Makes sense, right? So you can apply the same reasoning to all of these terms. If you see one that doesn't make any sense, that means the derivation of that particular term has an issue. But if you can trace your way back, because you did it step by step, you can probably spot where you made a mistake and go like, oh, okay, I forgot something or do something incorrectly. But I'm suspecting that I have two terms that are really not needed here. Either that or my 14-term solution is actually wrong. But,
You get rid of the first term because it's duplicated.
because of what?
It's written 2 times.
Oh, okay, it's duplicated.
Yeah.
Because we have A, B, C, D.
4 parentheses, yeah, there.
This one?
Um,
This one has got a negated
no,
A.
the one before.
This one?
Sorry, it was too small.
Well, I'm sure, probably one of these can be simplified. Like, if, okay, A, not D. Well, you don't have to simplify everything. This is perfectly okay as an answer. Hmm? Say again?
You do what I did, didn't simplify anything.
Well, then you end up with what, 32 terms?
I probably have like 40. No.
You mean for Z2 specifically? That's crazy.
But are there
It
any
works.
questions about the steps of doing it? If I'm not talking at the same time, probably can get it done a little bit faster. But that is the process. Now, did you guys go through about the same thing, or
Yeah.
was your process different from mine?
It's pretty much.
Pretty much.
The only difference I had was that choosing to distribute versus apply to Morgan's, like in what order you do. Does it all kind of work out the same? Or?
Yeah, they all work out the same. Yeah, because you just have to, because sometimes you can choose which one to use first. You can do De Morgan's law on the inside first, or you can apply, the distributive law on the outside first. So the ordering is up to you. Some people just have a specific way to do things. Like I like to do De Morgan's law first and then do the distribution. Some other people may decide, I like it the other way around. So there's no right or wrong, because it should all end up with the same type of equations. Okay?
That's 61.
Huh?
For Z or X.
61? Okay.
61 disjunctions?
Yeah.
Mother
Whoa!
goodness.
61 disjunctions. Okay, so the next question is, how many actual cases? Okay, because we have 64 possible cases, because we got 6 bits as input. So out of the 64 possible cases, how many ends up with Z2 as a 1? That's the question. So we can at least do a checksum and go like, okay, we should only have that many terms. Even if we spell out everything, like every single term has A, B, C, D, E, F in it, okay, that is the maximum. Okay, how do we know what is that number? We write a C program to figure it out. How do you write that C program? Okay, let me see how much you guys still remember from the C programming class. Okay, so I'm only doing this, as a sanity check. It's not really, the answer. We don't figure out the answer this way, but it's a good sanity check. All right, so let's go ahead and write this program. Okay, so I'll just call this program Z2. Okay, for obvious reasons. I'll include stdio main int x y and count. Okay. For x equals to, where should we start? 0 is a good number. X is less than 8 and plus x. Okay. Well, I haven't used C for too long. Okay, syntax error. Okay, but why do I choose this range? Why did I choose the range of 0 to 8 or 0 to 7? Because I get out when x is 8. Why? Because x is a 3-bit number.
Yeah.
What is the range of an 8-bit number? Of a 3-bit number, sorry.
0 to 7.
0 to 7, exactly. So that's why I'm going from 0 to 7, because I'm trying to figure out, for all possible combinations between x and y, how many of those sums end up with this bit being a 1. Okay? All right, so let's go ahead and work on the inner loop here. Okay, I like curly braces even if they're not needed. Y, same thing. Okay, so same range, because y is also a 3-bit number. Now, we can definitely add x and y, but I'm not interested in the sum itself. I'm only interested in one of the bits of the sum. So in this case, I'm going to say, well, there are several ways to say that. Well, I'm going to do the tricky one and see if you guys still remember the syntax. Okay, count has to be initialized. So I'm going to say count plus equal to question mark, a 1 and a 0. How do we call that expression? The one on the right hand side, this thing here. It's a ternary operator. Okay, and apparently, not everybody likes to use ternary operators, because there are multiple people who told me that they have not seen the ternary operator. You haven't seen that?
No, I did.
Huh?
Before, but now.
Oh, before this class? Okay, I personally really like the ternary operator because it's kind of like an if-then statement in an expression. And you can stick this expression in as a parameter or as an argument to a function call.
Yeah.
Whereas without this, you would need to really use a conditional statement, and then you have to duplicate a lot of stuff between two function calls, except for one of the parameters, or one of the arguments. So I personally really like ternary operator because it's very flexible. Okay, so when do I want a 1? When do I want to add a 1 to count, and when do I not to add a 1 to count? I want to add a 1 to count when z2 is a 1. Okay, well, that's based on the sum of x and y, but I'm not interested in the entire x and y. I'm only interested in one of the bits. Which bit are we talking about? Well, I call it bit 2, okay, because the least significant bit is bit 0, so this is bit 2. How do we get to bit 2? Well, you can say 1, 2, 4. 4 is bit 2, but I'm too lazy. I just say, hey, let's just shift bit 0 twice. That's bit 2. Okay? And if you worry about operator priority, just put parentheses around it. Now the question is, what do I put in here? Because on one side, I have a potentially 4-bit number. And on the other side, I have a bit mask, so that I can focus on just one of the 4 bits. How do I apply, what operator do I apply here, so that the answer is just saying, oh, okay, we are only focusing on that bit. Bitwise AND, okay, just a single ampersand. There we go. Now, I also saw somebody doing this in Java, and the Java compiler kept complaining. It's like, no, issue, you cannot do this. Why not? The Java compiler is more strongly typed than C. The C compiler looks at this and go like, x plus y is just an integer. Fine. 1 left shifted twice, it's just a number, just an integer. Integer, bitwise and integer ends up with an integer, not a problem. Then the C compiler sees, oh, this value is being used in a ternary operator. I need to treat this as a Boolean. This is where the two compilers behave differently. A C compiler is just going to say, integers, Booleans, and they're all the same. Anything that is non-zero is true, anything that's 0 is false. Not a problem. The Java compiler looks at things and goes like, no, integers are integers, Booleans are Booleans, not good. So it won't let you do it. So what you need to do in Java is actually to compare this entire end result with 0, because the result of a comparison is Boolean, it's either true or false. So that's the difference between the two compilers. So if you really want to make this code cross-platform and cross-language, compatible, fine, just do it this way. happy? That's my daughter's favorite phrase. Are you happy now? Well, it's not about me, it's about the compiler. And the compiler, the Java compiler is going to be happy about this because now you have a comparison, and the result of a comparison is a Boolean. Okay, and we just have to print the count out as the final result. And return 0, and we're all done. Okay? Now I'm shortcutting this entirely because in your case, if you want to figure out whether your equations make sense or not, there's a lot more stuff you can do on that line. Because if the result of this expression is actually non-zero, you can go ahead and print out the individual bits. Then you know exactly what bit pattern is going to make Z2 a 1. But once you know the bit pattern, you can reverse it back into a conjunction. That's another way to solve this problem, to do this homework. But I'm not sure whether this is more painful or less painful. Okay? Because some people can say this is actually more painful. Now, it is only less painful if you do this. If you look into the CIRC file of Logitsim, and you say, okay, now I understand how it is representing a gate, where it is, how many gates, which one is negated and whatnot. You can write a program like this to output and crank out a circuit file for Logitsim. In other words, you are writing a program to output the file that ends up to be your Logitsim circuit. Sorry?
Well, the circuit's an X amount, so it's pretty easy to parse.
Yes, it is easy to generate, easy to parse, easy to understand, but it will take you time to understand that format first. It will take you a few trials. But that's besides the point. It is one way to do your homework assignment. I did not mention it because I did not think anyone would actually thought about doing that. Okay, so let's just do this one. GCC-O Z2 Z2.C. Of course, being me, you should always use more null.
What about pedantic?
What about pedantic? Let's do it too. Pedantic. Okay, no complaints. And there are 32 cases. So if you end up with 62 conjunctions, you're guaranteed that some of those conjunctions can be combined. It doesn't mean it's wrong. Okay, it is possible that you might have duplicate terms, but these 32 will be fully spelled out terms, including all A, B, C, D, E, F already. So if you remove all duplicates, you should only have 32 terms. If you try to simplify and use the not here, then you end up with less than 32 terms. So if you end up with 60-something terms, you're guaranteed to have duplicates. Yep.
The thing is, you actually can't go above 32 because the OR gate that you use to pass it all through, 32 is the maximum of inputs you can have. So when I got to 32, I was like, oh shoot! But then I tested all of them, and
Well, can't you just hook that OR gate up to another OR gate, so you have two additional OR
But
gates?
then you have
so
the number of stages.
yeah.
You're
So
changing the number of
that's
stages.
the
Yeah.
that's the thing. 32.
You leave a comment. You're like, I came up with more than 32, it won't fit.
Actually, in that case, you look at the source code of Logitsim because it is an open source program, and you change that, so then you can have more than 32 inputs to the gate.
Will it
That's
load on
definitely the
your
reasonable thing to do in
machine
that
to fix it,
circumstance.
or will it just crash when you try to load it? Would- if
Well, you have to
modify the
go through the
program.
entire source
Yeah.
code and find out exactly where they put that hard limit of 32.
But your test case will still have the same hard code.
But
right?
my test cases is nothing more than just specifying A, B, C, D, E, F and see whether your answers are all correct or not. In other words, I don't really care how many gates you're actually using. I only care about that there are two levels. But of one single level, if you want to use 200 gates, hey,
But if you modify the program, will it work on another computer with a different version?
Ah, you have to redistribute that.
Yeah. There's no slot on Moodle for that.
We just attach another file.
You can attach it too, yes.
Use this version.
Well, I'm just gonna modify the program to always say that my programs are right then, if that's the case.
You just have to release the program. That's the whole spirit of GPL. Okay, so are there any questions about this homework? Are we ready to do the subtraction?
Let's do it.
Basically the same process except.
Exactly. It is the same process. So I might as well talk about the answer to the second question or the second homework assignment. The second homework assignment is asking you about the R, the result of a subtraction, and also the borrow function of a subtraction. Right?
Mm-hmm.
The one that has two tables when you have to fill it in. Okay. Okay. So let's go ahead and do that one. I'll just do it on the in the editor. Okay. So the question is, as far as R is concerned, okay, 0 minus 0 has a result of 0. 1 minus 0 has a result of 1. 1 minus 1 has a result of 0. The only tricky case is, what if I subtract 1 from 0?
It's 1. Yeah.
It is 1, exactly, with a borrow. But since this is just R, it does not represent the borrow, okay? Okay, now on the other side, I'm going to ask, what is the borrow of subtracting 0 from 0?
0.
I don't need to borrow, so there's a borrow of 0. 1 minus 0 has a borrow of 0. 1 minus 1 has a borrow of 0. And then 0 minus 1 has a borrow of 1. Okay. This is all good. Okay, that's the table. Okay, this is what you need to do for the other homework assignment. Is just to fill in those cells with zeros and ones. That's it. If I want to convert this into logic gates again, how do we express R and how do we express B?
R is exclusive R again.
Yep.
B is does not imply.
Ah, very good. You can use the other Boolean operators. Okay, very good. So R is the same. You're right. So R is basically just exclusive or as we do it, it's X not Y or not XY. Okay, kind of the same. It is the same as addition. Borrow, on the other hand, there's only one case to make it true. So that means you look at that one case and then you say, oh, so X has to be false and Y has to be true to make it true. Okay? So if X is false, what makes that true? Because we want to end up using conjunctions. So you just say, oh, if X has to be false to make it true, then not X is true because X is false. Y has to be true, so we'll just leave it alone. So B is really just not X and Y. Instead of X and Y, it is not X and Y. That's just one extra negation. Yep.
Or borrow.
Or borrow, yes.
And it's called what, like a...
It's the opposite of implies, right?
Okay, let's see.
Okay.
It's not the opposite of imply. Okay.
No?
Let's try to figure that out. Because I want to find out whether there's another way to say, not X, Y. Okay, let's look at what is implied. X implies Y means not X or Y. So if it is the negation of the whole thing, you apply the Morgan's law, so it becomes X and not Y, which is not quite what we want. So I think you can say it is not Y implies X. So you can re-express that thing as not Y implies X. Or Y does not imply X. Yep.
With the binary subtraction, is it the same as the addition where you can pretty much subtract A from B and B from A? Do it both ways?
It is not, no, it's not commutative anymore. Subtraction is not commutative. So you can't, well, okay. at the level of conjunction and disjunction, yes, you can still have commutation because those operators are commutative. But at the arithmetic level, when you're dealing with subtraction, it is not commutative. Is that?
Yeah.
Okay. But how is this going to impact your answer? Yep.
Well, for one, like the positioning of the positioning of the since it's not commutative, the positioning of like where the different bits lie is really important.
Yeah, but it does make certain things more complicated than it is now. Because if we just look back at the expression that we are dealing with here, if I turn this into a B instead of a C, to figure out the borrow flag, then we have more of a problem because one of these things has to be negated. Like in this case, the first one has to be negated, which means you have one extra level of applying the Morgan's law. So it's going to be a little bit more complicated than addition. Yep.
You told me last week that subtraction.
Well, it's about as easy.
All right.
But it's really just that difference, okay? The only difference is the borrow function where you have to negate the x instead of xy. It is the negation of x and y. Okay.
So just one. Or
Yep.
one.
Okay, but why are we doing this? Why did we spend about 1 hour and 10 minutes to talk about this? What is the significance of all this stuff here? Other than it's so painful.
Shows your hate for us.
But why do we do this? Okay, many people looked up stuff. Okay, they looked up, how to make a 3x3 adder, and almost every single person, or at least the first few links, talk about, these are half adders. You put two half adders together, you get a full adder. You stack up 3 full adders. You hook up all the carry wires, and now you have a 3x3 adder. Okay, how come a Google search returned those results when you look up a 3x3 adder instead of this?
It's easy.
Nobody does this.
This is not conventional.
Because this is not academic. This is what Intel does.
Huh.
Okay, the carry ripple method, which is 3 full adders. You take the carry out from one, you feed it to the carry in of the next one. You take the carry out of that one, you can put it into the carry in of the next one, and so on. That is quote unquote academic. But nobody in industry is going to do adders that way. Because, well, you guys read the material already. The delay, the number of gates between the input to the last carry output of a carry ripple 3x3 adder is 9 propagational delay. What about this method?
Yeah, but the length of the wire that goes all the way to the most bottom thing, that takes time too.
No.
No,
Not nearly
because
as
they all
much.
happen in parallel. Okay, so let's take a look at the picture or schematic, kind of concept picture. Okay, so what we have with these equations are input pins, right? A bunch of input pins, bunch of conjunctions, okay? And we can now end up with what, 14 or more of these things, and they go connected everywhere like this, right? Okay, massive connections. But these can all happen at the same time. When I change these pins, it's changing the input of all of these input of all the conjunction gates at the same time, right? So they're all changing at the same time. They come up with the answer at about the same time. What do we do with the output of these conjunction gates or AND gates? There's an overall OR gate that takes the output of all of these things. So how many gate propagational delay do we have? 2.
What I was saying is that the length of the wire that only reaches one end and then come back.
But
It doesn't come
Goes
back.
through.
It only goes in one direction. It only goes through 2 gates to the actual output. 1, 2, output.
But what about the power that you're wasting in order to provide all these gates that potentially are not going to even turn on?
Well, do you want your 3 gigahertz Pentium i7 processor, or do you want it to be 500 megahertz?
Yeah, if it's 500 megahertz and it's really quick, then
It's
like
not
kinda
going to be
like
quick.
Apple,
You're
right?
talking about a 2-gate delay versus a 9-gate delay, and we're only talking about a what? 3x3 adder. Do you want your i7 processor to only be able to add a 3-bit number to another 3-bit number?
No, I'm thinking.
Okay, so now let's stretch this out. Okay, let's stretch this out to a 64-bit adder. Okay, because we all like 64-bit processors. The first stage is going to take, I think, 5-gate delay, and then each additional one takes 2-gate delay. That's the equation. So with a 64-bit adder, we are looking at 5 plus 63 times 2, maybe 62, but the number is there about. Okay, so we're looking at 126 plus 5, about 130. Okay, we're talking about 130 gate delays. Okay, so if we look at the amount of time of the signal change on one side to become effective on the other side as 1 unit. Okay, this will take 130 units to compute the sum of 2 64-bit numbers. Okay, doesn't sound too bad. But using this approach, if I use this approach for a 64-bit adder, what is the amount of time? 2.
What's the amount of gates?
Well, that's why we need 18 nanometer, transistors. That's why we need to pack all that stuff in. Because if Intel doesn't do that, AMD is going to do it.
Yeah, they probably do.
Yep.
And on top of that, Intel's probably not restricted to specifically AND and OR gates, right? So they could have a few left.
They
A
have
few
to
less.
use whatever gate is native to the substrate and the process. So they have more physical constraints. So they will look at the number of wires that they have to cross over and stuff like that, because they may run out of routing resources before anything else. Because you have to route one of those pins to many other pins now. So they can run out of pins first. Routing resources first. So they have their own constraints, but the concept is still the same. They want to be able to do 64-bit by 64-bit add as quickly as possible. This is the quickest way. Now, you may not actually end up with NAND gates, OR gates, AND gates, OR gates, and stuff like that. They have to deal with whatever gate is native to the process of making processors. Because the substrate material is an N substrate material. And what is natural, what can be small and be made inexpensively, I don't know that part. Okay, I don't understand device physics well enough to say, oh, this is the kind of gate that they use. But the approach is still the same. They want to be able to do all the computations as quickly as possible. The gates are interchangeable. Okay, if I can express this using AND gates, you can do the same thing with NAND gates. You can do the same thing with OR gates and so on. That's just a transformation of the formula. But the concept is still the same, is to figure out 1 bit of the entire 64-bit sum. You take all the inputs, and then you only go through 2 or more, maybe 2 or 3 gate levels, and then you have the answer. And that's the fastest way to get the result of an adder. Because otherwise, you're looking at a difference of 60 times. You can no longer do one computation per clock within the ALU. So now whenever your ALU is doing computation, the rest of the processor has to hold still and I cannot do anything, because we have to wait for the result of the adder. Then you can proceed and do something. So it doesn't matter how fast your clock is clocking, because you still have to wait 130 units of time to get the result out of the adder. Is that okay? Does everybody kind of at least understand the rationale behind doing something like this.
Yeah.
Yep. Okay, very good. Yep.
So it's gonna waste more power, which is present now. I mean, my laptop doesn't last very long, but it's got a very strong processor. And
I'm
it's fast.
not really sure about the wasting of processing power because you do have more gates, but they're operating at the same time, and they only have to operate for 2 cycles of time, whereas the other one has to operate for 130 units of time. Now, if you count the number of gates, yes, this approach definitely would use up a lot more gates than the other approach,
But it's faster.
but it's way faster. Are there any questions? Well, can we just make a compromise? In other words, instead of making a 64-bit by 64-bit adder using this approach entirely, can we marry the concept of carry ripple with the concept of yes, yeah, we can do this to a certain level before it gets too complicated? And the answer is yes. Because instead of a full adder, now you can stack 3 by 3 adders. You can stack 4 by 4 adders. Okay? In terms of hardware, if it is feasible to only make up to, let's say, 16 by 16-bit, adders using this technology, well, that's okay. Break up the 64-bit adder into 4 chunks. Each chunk then would use this approach. Then how bad is that? Well, you're still, basically quartering this number. So it is still pretty significant. Well, I take it back. You're not quartering this number. Your number is going to be, because we have 2 levels here, so 8 instead of 2. Now you are changing it to 8. But that's a really good trade-off, because when you look at the 16 by 16 adder versus a 64-bit by 64-bit adder, the 64-bit by 64-bit adder is far more complicated than the 16 by 16. But if you stack, you're still not losing a lot. So so hardware manufacturers can trade off and say, okay, we don't want to go the entire way using this approach, but we can use a hybrid. Yep.
Is that why we have multiple cores sometimes?
No, multiple core is really multiple core, which means each core is a complete processor, minus the cache, because the cache is actually shared amongst the different cores. Well, depending on the architecture, but most people share the cache. So one core is really a full processor. Each full processor actually has multiple ALUs. In other words, it actually has multiple 64-bit adders inside one single core, and that's how you can do calculations in parallel. And that's also the technology behind hyper-threading. How many people have heard of hyper-threading? Okay, that's the reason why you get an i5 instead of an i3. Right? i5 now has hyper-threading, no, i7. Okay, hyper-threading is basically the hardware itself trying to look at the incoming instruction stream and try to order the execution of the instructions in a way to maximize the use of the ALUs. And it's trying to do it in hardware. Because sometimes, let's say you have multiple threads. Okay, it doesn't work when you have a single thread program. So you have 4 threads coming in. Okay, basically 4 programs running at the same time. Okay? Sometimes you can schedule things. Like this one, it wants to add at this time. This one wants to add at this time, and this time, and this time. So by carefully rearranging the order, I choose to execute this thread up to this point, and then that thread over there, and so on. You can overlap as much as possible so that you can maximize the use of ALUs on the processor. We'll talk about ALUs later. But that's the hardware doing it in real time. Do you guys know what is the gain of hyper-threading? What is the number that they report and say, okay, with hyper-threading, your typical average application will improve the performance by, and yet you pay that extra money for your i7 processor? 30%.
20?
30.
30?
Yep. That's Intel's number, 30%. But it clearly depends on what type of program you're running. Certain types of program do not lend itself to hyper-threading. and you may end up with like 5–10% of gain at the most. Okay, but that's basically the technology behind the scene, and we call that untitled threading. Okay, well, we are running out of time, and I don't have your next homework assignment typed up yet, but you already know what it is.
Is it still
Yeah.
the same format? Like
Yeah, same format.
Okay.
Yep.
So, question. Okay,
Do you want to be recorded?
not really.
Okay.
Well,